Alright, so here we go with the next part of Chapter 3, which talks about rational functions. I want to start off by graphing probably the most basic rational function, which is f of x equals 1 over x. And we're going to graph that using a table of values. So to start off, we have our table x and f of x. I'm going to plot the points where x equals negative 5, negative 1/5, say negative 1, 0, 1, positive 1/5, and 5. So we have, when we plug in negative 5, we have 1 over negative 5 is negative 1/5. Plug it in negative 1/5, we have negative 5. Plug in negative 1, we have 1 over negative 1 is negative 1. Plugging in 0, we have 1 over 0. We can't divide by 0, so this function does not exist at x equals 0. So we can write DNE for does not exist. You can also write undefined. Plugging in 1, we have 1 over 1 is 1. Plugging in 1/5, we have 1 over 1/5 is 5. Plugging in 5, we have just 1/5. So plotting these points, we have negative 5, negative 1/5, that is right about here. Negative 1/5, negative 5 is right about here. Negative 1, 1. Positive 1, 1. 1/5, 5. And 5, 1/5. We can draw in the shape of the graph. And we have something that looks like this. Okay, don't forget your arrowheads. So the domain of this function, we can plug in any value for x except for 0. At 0, the function does not exist. So our domain is going to be everything except for 0. So we're going to denote that as from negative infinity to 0, but non-inclusive, and then from 0 to infinity. Our range, so for what y values do we hit? We hit every y value except for 0. So likewise, our range is going to be from negative infinity to 0, and 0 to infinity. Our asymptotes, we've got a vertical asymptote at x equals 0, and we've got a horizontal asymptote at y equals 0. Our end behavior, we can say that as x approaches infinity, our function f of x approaches a finite number. Let's see, as x increases, our function approaches, gets really close to 0. And as we decrease x, as we go towards negative infinity, as x approaches negative infinity, our function gets really close to 0 again, but now from the negative side. I want to talk a little bit about vertical and horizontal asymptotes. So here I've given you the definitions for each of these. So a vertical asymptote is the line x equals a, for which the function approaches positive or negative infinity as x approaches a from the right or left. So this first example, we're approaching a from the right, so from the positive side, our function is approaching infinity. As we approach a from the left, so from the negative side, our function approaches infinity. Or you could have as x approaches a from the positive side, from the right, our function decreases, approaches negative infinity. And as we approach a from the negative side, our function decreases or approaches negative infinity. For horizontal asymptotes, we have the line y equals b, for which the function approaches as x goes off to plus or minus infinity. So as x increases, approaches infinity, we get really close to this y value b. And as x approaches negative infinity, we get close to this y value b. Contrary to common misconception, a horizontal asymptote, the function can cross. It can cross. An example would be right here. We can see that it crosses the horizontal asymptote. However, a vertical asymptote, the function cannot cross, because that's where the function is undefined. So on the next page, I want to graph the function f of x equals the quantity 3x plus 5 over the quantity x plus 2 by using a table of values. So you can plug this into your calculator, or you can evaluate. When you plug in negative 4, we have 3 times negative 4 plus 5 is 7. And negative 7, and then we have negative 4 plus 2 is negative 2, so at negative 4 we have positive 7 halves. At negative 3 we plug in 3, and we get 4. At negative 2, when we plug it in, we get negative 2 plus 2 in the denominator. We get 0. So we can't divide by 0, so the function does not exist at x equals negative 2. Plug in negative 1, we have negative 3 plus 5 is positive 2. Negative 1 plus 2 is positive 1, so we have positive 2. Plugging in 0, our x terms cancel out, so we have just 5 over 2, 5 halves. Plugging in negative 10, we have negative 30 plus 5 is negative 25. Negative 10 plus 2 is negative 8, so we have 25 eighths. And then plugging in 10, we have 30 plus 5 is 35 over 12, so we have 35 twelfths. I've also included these two. So we notice that the function is undefined at x equals negative 2. So I wanted to see what's going on around x equals negative 2. So I chose 2.01, negative 2.01, and negative 1.99. I want to see what's happening just around where it's undefined. So at negative 2.01, we can evaluate. We get that the function is equal to 103. And then f of negative 1.99 is negative 97. So let's start graphing this. So we know that the function is undefined at negative 2. So we've got a vertical asymptote at negative 2. We also know, well, let's start plotting these points. We have negative 4, 7 halves. So we have negative 4 and then 3.5. So that's right about here. We have negative 3, 4, which is right about here. We have negative 1, 2. 0, 5 halves, so that's 2.5. Negative 10, 25 eighths. So that would be 3 and a little bit. So it would be like right here. And then we have positive 10, 35 twelfths. That's just under 3. We have negative 2.01, so just past this asymptote, we have a positive 103. So that's way, way up there. And then we've got negative 1.99 just before. We've got a negative 97, so that's way down there. So the shape of this graph should look something like this. Okay. We've got something that looks like this. Notice that the end behavior of this graph, we seem to be approaching a number, right? At x equals 10, it was just below 3. At x equals negative 10, it was just above 3. So on either end of our graph, we're getting closer and closer to this finite number. Our asymptote is going to be at y equals 3. Our domain, so for what x values can we plug in? We can plug in anything we want except for negative 2. So we can go from negative infinity to negative 2, and then from negative 2 to infinity. For our y values, what don't we hit? Well, we hit everything except for y equals 3. So we go from negative infinity to 3, and 3 to infinity. Our asymptotes we talked about, we've got our vertical asymptote at x equals negative 2, and our horizontal asymptote at y equals 3. Our end behavior, so as x approaches infinity, our function f of x approaches 3. And as x approaches negative infinity, our function approaches 3 again. So how do we determine the equation for our vertical asymptote? Well, looking at the function, we can determine it because it is where the function is undefined. So wherever the denominator is equal to 0 is where we have a vertical asymptote. How do we determine the horizontal asymptote? Well, the way that we've been determining it so far is we've been looking at the end behavior. So what does the function approach as x grows very, very large in both the positive and negative direction? So you can either look at the end behavior, or you can use the dominant term rule, which we will learn right now. So the dominant term rule says that if r is a rational function, where, and I'll go ahead and write out what r could be, so r of x is equal to a polynomial over a polynomial. So we'll say that we have an x to the n plus an minus 1 x to the n minus 1 plus all the way to you have a1x plus a0. So that's the numerator, that's the polynomial. That's just the definition for polynomial. And then over another polynomial, so we'll use b and m this time. So bmx to the m plus b to m minus 1 x to the m minus 1 plus all the way to b1x b0. So again, definition for a polynomial. So r is a rational function of a polynomial over polynomial. Then we can determine the vertical asymptote right, which we already know. It's where the denominator is equal to 0. So we can say that the vertical asymptote is at x equals c, where c is a 0 of the denominator. So when you factor the denominator, if you get x minus c is a 0, then at x equals c, that is the equation for a vertical asymptote. What about the horizontal asymptotes? Well, we consider three cases. The first case is if n is less than m. So we're saying that if the degree of the numerator is less than the degree of the denominator, so if the degree of the denominator is greater than the degree of the numerator, then the horizontal asymptote, I'll abbreviate HA, is at the line y equals 0. Case 2 is if we have n equals m, so the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is at y equals the ratio of the leading coefficients, an over bm. So if we take those leading coefficients and find the ratio, then that is the equation y equals for the horizontal asymptote. And finally, if n is greater than m, then our horizontal asymptote, we don't have a horizontal asymptote, so there is no horizontal asymptote. The reason why that's true is if the degree of the numerator is greater than the degree of the denominator, well, think about the end behavior. The numerator is going to blow up much larger than the denominator, so it's going to diverge off to infinity. Let's try example 2. Here I've got a rational function. Let's start off by finding the zeros. So remember, the zeros, both real and imaginary, are where the function equals 0. In order for this rational function to equal 0, it's the same as saying if the numerator is equal to 0. So we can say that the zeros are where the numerator, 2x squared minus 4x plus 5 is equal to 0. Unfortunately, we can't factor this trinomial, so we're going to have to use the quadratic formula. So we have x equals negative b, so 4, plus or minus the square root of b squared, 16, minus 4ac, which is 40, all over 2 times a, so 4. When we evaluate this, we get 2 plus or minus I root 6. So we've got two zeros here, 2 plus or minus I root 6. Our y-intercept is where x equals 0, so we're finding f of 0. So we plug in 0, we have 2 times 0 squared minus 4 times 0 plus 5 all over 0 squared minus 2 times 0 plus 1. We get all of our x terms cancel, so we just have 5 over 1, our constants. So our y-intercept is at 0, 5. Our asymptotes, again, our vertical asymptote is where our function is undefined, where our denominator is equal to 0. So let's take a look at our denominator. I recognize that we can factor this denominator. So we can say that this is 2x squared minus 4x plus 5, that stays the same, over our denominator. When we factor this, I know this is a perfect square trinomial of x minus 1 squared. So then, where this is equal to 0, where our zeros are, is at x equals 1. So we've got a vertical asymptote at x equals 1. In order to find our horizontal asymptotes, we have to look at the degree of the numerator and the denominator. Well, the degree for the numerator is 2. The degree for the denominator is 2. They're equal, so we can use rule 2 of our dominant term rule for our horizontal asymptote. So we take the ratio of the leading coefficients, so 2 over 1. So we get the equation of the line, y equals 2. So right away, we can draw in those asymptotes. We have one at x equals 1. We have one there. And then we have one at y equals 2. So let's talk about what's going on between the near the asymptotes. So for any of these, I always want to see what's happening to the function right next to the asymptote. So for any of these, I'd like for you to write out this table. So as x approaches, so we're going to say as x approaches the asymptote. And so our vertical asymptote is at x equals 1. So we're going to say approaches 1 from the positive side and approaches 1 from the negative side. And we're going to use these superscript plus or minus. In the next row, we're going to say the sign of f of x. So what's going on with f of x? And then we'll say, so f of x approaches something. So as x approaches 1 from the positive side, we're saying that as x gets really, really close to 1 from the positive side. So we're going from, say, 1.5 to 1.1 to 1.01 to 1.001. We're getting closer and closer to 1 from the positive side. So as we get closer to 1 from the positive side, our numerator, as we get closer to 1, we have, this is like 1 squared, so we have 2 minus 4 plus 5. This whole quantity is going to be positive. So our numerator is going to be positive. Our denominator, well, if we're approaching 1 from the positive side, we've got just over 1. So we plug in just over 1 for x. So we have like 1.01, for example. Minus 1, that's still going to be a positive quantity. And then we square it, it's still going to be positive. So our denominator, as x approaches 1 from the positive side, is still positive. Now what about when x approaches 1 from the negative side? Well, still our numerator is still going to be positive, right? So if we're talking, we're getting close to 1, so 0.95, 0.99, 0.999, and so on, getting really, really close to 1 from the negative side. So we plug in that, and our numerator is still going to be positive. So we still have a positive quantity here. But then in the denominator, we have, say, 0.99. Plug in that. Minus 1, you have a negative 0.01. But then we square that, and that becomes positive. So our denominator is still going to be positive. So we're saying, as we approach 1 from the positive side, our function is a positive over a positive. it's going to be approaching infinity. As we approach from the negative side, we have a positive over a positive. It's going to be approaching infinity. So let's start to graph these. So again, we've got our y-intercept of 5. So 1, 2, 3, 4, 5. We've got a point here. Let's get a point on the other side of the asymptote. So we have 1, 2. Let's find f of 2. So I'll plug that in down here. F of 2 is equal to 2 times 2 squared minus 4 times 2 plus 5 over 2 minus 1 squared. So this would be 4, 8 minus 8 plus 5 over 1. So we have 5. So we have the point 2, 5. So then we're saying, as we approach 1 from the positive side, so as we come in from the right side, we're going off to infinity. So we're going to be going up, and then it's going to level off near the asymptote. As we approach 1 from the negative side, we're also going off to infinity. So as we're getting closer and closer to 1, we should be increasing, going off to infinity. So we have this behavior here. So that's a sketch of this graph here. Let's talk about domain and range. So domain, what numbers can we plug in? We can plug in anything except for x equals 1. So we can say that our domain is from negative infinity to 1 and from 1 to infinity. Our range, for what values does our function hit? It hits everything above y equals 2, but not including y equals 2. So we have our range is from 2 to infinity. And then our end behavior, I'm going to introduce a new notation for the end behavior. We're going to use limit notation, which is, we're going to be getting a lot of practice with limits, both in this chapter, but also in next chapter, in chapter 13. We talk about limits. So I'm going to say the limit of f of x, so lim f of x, as x approaches infinity, so we're going to write that underneath limit. This says the limit of f of x as x approaches infinity. This is saying what happens to f of x as x approaches infinity. So the limit of f of x as x approaches infinity, well, that's just like our end behavior. As we approach infinity, our function gets really close to y equals 2. And then what happens in the negative direction? So the limit of our function, what happens to our function as x approaches negative infinity? Well, as we move in the negative direction, our function approaches y equals 2 again. Let's try this next example. Here I've got a rational function. I've got a quadratic in the numerator and a quadratic in the denominator. The first thing I want to do, and I recommend for any of these, is just to factor where you can. So let's take a look at the numerator. We've got x squared minus 3x minus 4. This can be factored into its factors of x minus 4 and x plus 1. The denominator, we can pull out a GCF, so we can pull out a 2x, and what's left is x plus 2. So again, the zeros for this function is where the function crosses the x-axis, or where it equals 0. In order for this to equal 0, the numerator equals 0. So we've got zeros at positive 4 and negative 1. The y-intercept is where the function is equal to 0. So we have 0 minus 4 times 0 plus 1 all over 2 times 0 times 0 plus 2. When we evaluate this, we get negative 4 over 0. We can't divide by 0, so the function does not exist at x equals 0. So there is no y-intercept. We know this from the asymptotes. So the vertical asymptotes is where the denominator equals 0. Well, using the zero product property, we find that that is at x equals 0 and x equals negative 2. So that's why we don't have a y-intercept, because we've got an asymptote at x equals 0. To find our horizontal asymptote, we look at the degree. So this is degree 2 over degree 2. Since it's the same, we can take the ratio of the leading coefficients, 1 over 2. So we have the horizontal asymptote is the equation y equals 1/2. So we can go ahead and plot those. We've got a vertical asymptote at x equals 0. Another vertical asymptote at x equals -2. We've got a horizontal asymptote at y equals 1/2. We've got zeros at +4 and -1, so a 0 here, and a 0 at +4, 1, 2, 3, 4. We don't have a y-intercept. So let's see what happens near the asymptotes, particularly the vertical asymptotes. So as x approaches, let's take a look at our first vertical asymptote, 0. And we're going to say 0 from the positive side and from the negative side. And then we're going to take a look at our second asymptote, -2, from the positive side and the negative side. And we want to see the sign of f of x and then the end behavior of f of x. So let's take a look at where x is approaching 0 from the positive side. So you can plug in 0 here. We have 0 minus 4. That's a negative quantity. So we can put that's negative. We have x plus 1. That's going to be a positive quantity as we approach 0 from the positive side. Down here we have 2 times 0 from the positive side. That's like 0.01. It's getting close to 0 from the positive side. This is going to be a positive quantity. And 0 plus 2, that's going to be a positive quantity as well. So we have a negative times a positive, all over a positive. We're going to be approaching -infinity. How about 0 from the negative side? We have 0 minus 4, that's going to be a negative quantity. 0 plus 1 is going to be a positive quantity. We have 2 times 0, but from the negative side, so it's going to be a real small 0, close to 0, small negative, but it's going to be times 2, so it's still going to be negative. So we have a negative here. And then 0 plus 2, that's going to be a positive. So we have a negative times a positive over a negative times a positive. Those negatives are going to cancel out. We're going to be approaching infinity. Next up, we're going to look at when it approaches -2 in the positive direction. So -2 minus 4 is still negative. -2 plus 1 is still negative. -2 times 2 is a negative quantity. And then -2 from the positive side, so like -1.99 plus 2, that's going to be a positive quantity. So we have a negative times a negative is positive over a negative. We're going off to -infinity. And last but not least, we have -2 from the negative direction. Again, this quantity is going to be negative. This quantity is still going to be negative. This is going to be negative. And then this, -2, but a little greater, so -2 plus 2, it's going to be a little negative. So everything is negative here. So double negative over double negative is a positive. So we're going off to infinity. So graphing this, let's graph. So as we approach -2 from the negative side, we're going to be going up to infinity. So we want to be going upward as we're approaching our asymptote at -2 from the negative side. From the positive side, we want to be going from -infinity. So we're going to start down here. And then for 0 from the negative side, we're going to be going off to infinity. So we want to go from -infinity to +infinity. So we're going to be going up, we're going to pass through our x-intercept, and we're going to go through up to infinity. And notice we cross the horizontal asymptote here. Last but not least, 0 from the positive side, we're going to be going off to -infinity. So coming at 0 from the positive side, we want to go to the -infinity. So that's going to be approaching the asymptote in this manner. So we get a graph that looks like this. The domain of this function, well, we can plug in anything except for 0 and -2. So we want to say we can go from -infinity to -2, and then from -2 to 0, and then from 0 to infinity. The range, well, we can plug in anything. we can get anything from our function. Particularly in this middle section, we actually hit all real numbers. So our range is from negative infinity to infinity. Last but not least, our end behavior. So we're going to use our limit notation. As x approaches infinity, our function f of x goes and it approaches 1/2. And likewise, the limit of f of x as x approaches negative infinity. As we move to the left, we are approaching 1/2. All right. So this is part 1 of rational functions. We're going to get a whole lot of practice on this. Join me again next time in part 2. Have a great day, everyone.